Hi all, let's look at this optimization problem in section 4.5. In this one, we have a square-based box-shaped shipping crate is designed to have a volume of 80 cubic feet. We know that the material used to make the base costs twice as much per square foot as the material to create the sides. And the material to create the top costs 1/2 as much as the material to create the sides. We're supposed to find the dimensions of the crate that minimize the cost of the materials. Okay, so the cost of the materials is going to be created by the cost times the surface area of the amount of each material. Before we get into that, though, we first have to get the dimensions of our box in terms of one variable. Now, we know that the base of the box here is given as a square, so I would let each side of the base of the box just be a square sides x by x. Now, I called the height of the box y. We know that the volume of a square cube like this would be the area of the base times the height, or x squared times y. So now what I did with that is I went ahead and created my volume equation here, set it equal to 80, since we knew that that was the volume mandated in the problem. And then that enables you to solve for y in terms of x here. We can say, well, y is just going to be 80 divided by x squared. That's going to be helpful to get our cost function just in terms of x. Now, speaking of that cost function, the cost is going to be the amount of cost times the surface area. Well, we have three different costs throughout this. I'm just going to call the cost of the base, since it said it's twice as expensive to do the base as it is the sides. I'm saying, well, area of the base is x squared times the cost. Well, whatever the cost of the sides is, this is 2 times that cost. Now, plus the cost of the sides. Each of the sides are going to have a base of x and a height of y. You have 4 of them, so that's why I have 4xy here. Now again, I'm just saying the cost of that is just 1 unit, and so, but I have 4 of them. That's why I have a 4 out in front of this. This is a 2 out in front of this one because it's twice the cost of each of the sides. And then plus the cost of the top, it said it costs half as much as the sides. So I said, well, 1/2 times whatever the area is there, which is 1/2 x squared. Okay, now that is the cost function in terms of x and y. I needed to get the cost function in terms of x. Well, that's where we let y equal 80 over x squared. You can say, well, if y is equal to 80 over x squared, then your cost function is going to end up just being 2x squared plus 1/2 x squared for 5 over 2x squared. This 4x times 80 over x squared simplifies to be 320x to the negative 1. Now, we need to take the derivative of that and set it equal to 0 to find the critical points that could yield a minimum for the cost function. So I can say, okay, take the derivative here. Derivative of 5 over 2x squared is going to be just 5x. The derivative of 320x to the negative 1, that gives me minus 320x to the negative 2. Notice I went ahead and wrote that as minus 320 over x squared. We set that equal to 0. What I did at that point, and there's no need, you shouldn't have to show it, I just multiplied both sides of the equation by x squared. When I do that on the right, it's still a 0. When I do that on the left, I get 5x cubed minus 320. Now we try to set the x equal to 0, so I move the 320 over to the right. When I do, it goes to a positive. Divide by 5 on each side, we get x cubed is equal to 64. Take the cube root of that, you get x equals 4. So what this is telling me is that the minimum occurs when the base sides have a length of 4 feet. And now to solve for the corresponding height, you just go back up here into your equation, actually this equation, and say, well, y is equal to 80 divided by 4 squared. That's 80 over 16. I get the 5, which tells me that the height of my box should be 5 feet for the uniform height all the way across this cube. Okay, that's a pretty good problem. Now, the only thing that I didn't do here is to absolutely prove that 4 is minimizing and not maximizing the cost. There's a couple of different ways if you wanted to check that, and you don't have to, but if you wanted to check that, you could use the first derivative test and find out that your first derivative is positive before, sorry, it'd be negative before 4 and positive after. So we would know that your 4 is a point that is a minimum cost. The other way you could do it is you could take the second derivative and you would see that your second derivative is going to end up being positive. And then you could say, okay, well, that's positive means that the function is concave up. Concave up, it has to be U-shaped. And then the critical point that's at 4 has to be a minimum. So you don't have to show that. You could do that. But as far as the solution to the problem, we would just need to get that base is 4 and the height is 5. All right, guys, pretty good problem.